Welcome to our educational podcast, where we embark on a journey through the captivating world of mathematics. Join us as we unlock the secrets of this beautiful discipline, revealing the hidden patterns and creative elements that inspire mathematicians around the globe. If you're passionate about learning and discovering the wonders of math, make sure to subscribe for insightful lessons that elevate your understanding and spark your curiosity. Mathematics is often described as a creative and beautiful discipline, a notion that might sound surprising at first. But think about it, at its core, mathematics describes the world in elegant ways, providing a framework to understand everything from the simplest shapes to the infinite vastness of the universe. Mathematicians talk about beauty in terms of elegance, symmetry, and the connections that weave different mathematical concepts together, creating an intricate tapestry of thought and discovery. Just like art or music, mathematics possesses aesthetic qualities that can invoke a sense of harmony and wonder. Paul Dirac, a famous physicist, once eloquently remarked that the beauty of mathematics is unmatched in its utility to understand the universe. This perspective is echoed by notable mathematicians like G. H. Hardy, who penned essays advocating the idea that mathematics is closer to art than to science. So, what is it that makes mathematics so beautiful? One answer lies in its patterns. Mathematical patterns are regularities or sequences that follow predictable rules. They emerge everywhere, from simple number sequences like 1, 4, 9, and 16, to the intriguing geometric shapes characterized by symmetry and tessellations. Plus, they are essential in nature, as seen in the Fibonacci sequence, a pattern that, for example, describes the arrangement of leaves on a stem, the spiral of seashells, and even the breeding patterns of rabbits. The search for these patterns often serves as the launching pad for mathematical discoveries. Exploring how mathematics applies to real-world scenarios helps us predict outcomes, discover new relationships, and grasp the underlying order of our universe. Richard Feynman, another physicist, reflected that there are structures in nature defined by simple rules. By studying these structures and their patterns, we bolster our understanding of the world around us, which brings us to the next idea: symmetry. Symmetry in mathematics refers to how certain shapes, objects, or equations remain unchanged through specific transformations like reflection, rotation, or translation. For instance, consider a square. You can fold it neatly along several lines, and it aligns perfectly, showcasing what's known as reflection symmetry. Rotate a square by 90 degrees, and it looks identical, demonstrating rotational symmetry. Symmetry is not merely an aesthetic feature, it's practical as well. It simplifies complex problems and highlights underlying structures. Moreover, symmetry is prevalent across various fields, spanning nature, art, architecture, and science. Group theory, which is the mathematical study of symmetry, has profound implications in areas like physics, chemistry, and even cryptography, revealing how interconnected these disciplines are. Moving beyond symmetry, we arrive at one of the most fascinating concepts in mathematics: infinity. Infinity represents something endless or without bounds, and it captivates mathematicians because it challenges our understanding of quantity and scale. What many may not realize is that there are different sizes of infinity. For instance, consider the set of counting numbers, which is countably infinite, meaning you can list them in a sequence. However, the set of real numbers, which includes all the fractions and decimals between those counting numbers, is uncountably infinite and even larger infinity. This groundbreaking idea was introduced by George Cantor in the 19th century, fundamentally shifting the landscape of mathematics. Infinity intertwines with concepts found in calculus, geometry, and even philosophical discussions about the nature of existence. A quick fun fact: the symbol for infinity was first introduced by John Wallis in 1655 and is believed to resemble a lemniscate, or a ribbon. Now let's turn our attention to a mathematical concept that beautifully intersects art and nature: the golden ratio. This magical number, roughly equal to 1.618, demonstrates a specific proportion whereby dividing a line into two parts results in a stunningly harmonious relationship between the whole length and its longer segment. Often symbolized by the Greek letter phi, this ratio is found in various settings: sunflowers, pine cones, and even renowned works of art like the Parthenon and the Mona Lisa. The golden ratio is revered for mathematically embodying beauty, inspiring artists and architects alike to create compositions characterized by balance and harmony. It's fascinating to learn that Luca Pacioli, an Italian mathematician, once referred to this ratio as the divine proportion, writing about its mystical properties in his 1509 treatise. Now, let's delve into another topic that reveals the elegance of mathematical creation: fractals. Fractals are geometric shapes that showcase repeating patterns at progressively smaller scales, leading to an infinite depth of detail. Generated through simple mathematical rules, these shapes create complex and stunning images, noticeable throughout nature in coastlines, snowflakes, ferns, and mountain ranges. The Mandelbrot set is perhaps the most celebrated fractal, known for its breathtaking visual complexity. Beyond their visual intrigue, fractals have real-world applications, utilized in computer graphics, signal processing, and even medical imaging. Did you know that the fractal nature of coastlines means their total length can vary based on the ruler you use to measure? The smaller the scale you use, the longer the coastline appears. Transitioning to the elegance of mathematical proofs, we find that an elegant proof achieves its result with clarity, simplicity, and insight. Such proofs reveal deeper truths, allowing connections to emerge across different mathematical spheres. Mathematicians value these elegant proofs, as they indicate a profound understanding of the underlying concepts, akin to appreciating a beautifully written piece of literature or fine art. Paul Erdos, a prolific 20th-century mathematician, famously distinguished proofs he admired as being from the book, suggesting that such elegance is worthy of a divine source. Now, let's take a moment to acknowledge the enduring connection between mathematics, art, and music. This relationship has existed for centuries. Artists frequently employ mathematical principles, such as geometry and proportion, to achieve depth and balance in their work. Music is inherently mathematical, rhythm relies on counting, scales depend on mathematical ratios derived from frequencies, and harmony reflects relationships between notes. Pythagoras, the Greek philosopher, uncovered the fundamental ratios tied to musical intervals based on the lengths of strings. Interestingly, some research indicates that listening to specific mathematical and musical patterns, often referred to as the Mozart effect, may enhance spatial reasoning abilities, underlining the intrinsic connection between math, art, and music. Lastly, it's vital to explore how mathematical ideas catalyze scientific discovery. Historical instances show how mathematical concepts paved the way for significant breakthroughs, sometimes even a century before their scientific counterparts emerged. Non-Euclidean geometry, for instance, was developed in the 19th century and later became essential for understanding Einstein's theory of general relativity. Similarly, complex numbers, once sidelined as mere imaginary constructs, are now indispensable in quantum mechanics, while group theory predicted subatomic particles' existence before they were ever experimentally observed. The pursuit of pure mathematical beauty, therefore, routinely yields profound insights into the physical world. Eugene Wigner famously remarked on the unreasonable effectiveness of mathematics in the natural sciences, highlighting how mathematics, developed independently, often reflects the realities of nature in astonishing ways. In conclusion, mathematics isn't simply a series of formulas and equations, it represents a vast landscape of creativity, discovery, and beauty. At every turn, we encounter the elegance of patterns, symmetry, and infinity. We derive inspiration from the golden ratio, explore the realms of fractals, and embrace the elegance of proofs. Mathematics is a creative discipline that encourages us to ask questions, discover new ideas, and appreciate the intricate connections that resonate through our universe. We can all find beauty in math when we view it as a compelling form of creative expression, connecting us to art, nature, and the scientific exploration of our world. Today, we explored the profound beauty inherent in mathematics. We discovered how mathematicians engage with concepts like patterns, symmetry, and infinity. The golden ratio illustrated nature's artistic harmony, while fractals showcased complexity from simplicity. We learned how elegant proofs reflect deep understanding, highlighting connections between mathematical ideas, art, and music. Finally, we appreciated how mathematical theories inspire scientific discoveries, weaving a rich tapestry of creativity in the quest for knowledge. Mathematics is not just a discipline, it's a window into the beauty of the universe. Thank you for joining us on this enlightening journey through the beauty of mathematics. We hope this discussion has inspired you to view math as a creative and vital part of our world. Don't forget to subscribe to our podcast for more exciting lessons, and as always, keep exploring and questioning the wonders around you. Until next time, happy learning!